I am honored to present the talk of my former student, Octavio Agustín-Aquino, which is not here due to the time it takes to get a visa in Mexico, more than 30 months. But anyhow, we are very pleased to have him in this in his lecture, a projection-oriented mathematical model for second species counterpoint. So, Octavio, most welcome. Please begin.
Well, thank you very much. I'm very grateful with Mariana and Emilio for their very valuable help, and in general, the organizing committee of the MCM 2022 and the scientific committee, of course. Well, and so let's proceed. Everybody can see my presentation, right? I think it's on my right. Yes. Well, it's a projection-oriented mathematical model for the second species counterpoint. It's a projection, oriented and a mathematical model. It's not the only one that could be formulated, but I think there is good reason to think this is a good one. But you readily see that some other is possible within the same framework, I would say. So this will have 4 parts: an introduction, one brief review of the first species model, the second species model that we're introducing with this. They are introducing with this model, and some final remarks. So, Guerino Mazzola's counterpoint model is founded on the concept of a strong dichotomy. And this encodes the notion of consonance and dissonance. And we'll tell a little bit more about this later. And counterpoint symmetry, which is the carrier of contrapuntal tension and allows us to deduce the rules of counterpoint within this model, of course. I'm sorry because I didn't realize that I would not be able to draw or underscore, but well, I think everybody can see my pointer, I think. Yes, okay. So strong dichotomy, this is the combinatorial part, I would say, of the model. It's something that I particularly like and I have been studying for a long time. And counterpoint symmetry, this is more specific to this model. And this is the difficult thing. Oh, sorry. To generalize, and in fact, I think somehow we have to drop it in for future modulation. But well, in this case, it is possible to do it. So, what's the problem with Mazzola's model? Well, what we have been remarked several times by now, that it is restricted so far for species counterpoint. There's a single note against a single note, and it doesn't matter how much it lasts, as long as it is one note against one note. So we need to increase the potential, so extend this model for analysis and composition, so it is indispensable to go first for a second species counterpoint model, and further, if possible. In principle, this could be done with this model as well, the same idea, and I think it's future work to prove that actually this basically extend. Well, no, I would say extend. I would say that particularizes. Sorry, it's for the first so to the first species model. So and it would be a good, I would say, conclusion of the program, because it's. I remember Sachs, and I think also Fuchs himself tells us that the model, the first species is the fundamental, I would say, theory for the counterpoint, in general. So our approach in this, for this as a first step, is to extend the notion of counterpoint interval to a through interval. So, and we have an algebraic object, and we'll see how can this be done. And in fact, that's the thing, that we can do this in several ways. And well, I must say that I began working with this in 2008, 2009, and it has been a long time since I first reflected on, well, I concentrated on this. So I really don't remember sometimes how I came up with some of these things among many other possibilities. And I think I will need to reconstruct this work. I don't know if you're aware, but there is a paper with Juan Sebastián Arias and Emilio, and where we analyze all these possible variations for the model, for the original first species model. So a similar thing can be done here, but with some extra complication that you also the weight you can attach two tones to one tone. There are much more possibilities. So, but the point here is that first one should be on the downbeat and second one in the upbeat. Sorry, I don't remember right now, but I think I'm using the Fuchs naming convention that downbeat comes first and the upbeat comes later. I think it's the opposite sometimes in music literature. So for our extension, the main idea is that the counterpoint symmetries in this case do not determine another two interval successor, but a first species interval, the downbeat. We want this because we want to blend species. Because, for instance, if one two interval determines another two interval, then we have to discard. If we want to go back to first species, we will need to discard the other interval. So I think that would be more natural than this approach. And we'll see that it's founded on what Fox himself writes, and I think it's quite it goes along quite well with the musical practice as well. So let's check the first species case again. I always have to sketch the first model at least, to the very least, because I'm aware that not everyone is familiarized with it, or well, I don't know, perhaps. I see a lot of familiar faces. So I think some of you already know this, but anyhow. So since the 15th century, at least, perhaps a little bit later, but it's a good point of reference. In what comes to counterpoint, the intervals can be partitioned into halves, the consonances. Here is also a contentious point because some say, well, beyond the octave, how do you justify the identification of the octave identification? I would say, well, but because in the treatises they treat the intervals in the same way as if you have going down one octave, and so and in fact you cannot go much farther than one octave beyond in the interval. So I think it's a rather good approximation already for this century, but and later even more so. So the prime or octave, the minor third, major third, the fifth, perfect fifth, the minor sixth, and the major sixth are the consonants. Dissonances are everything else. Minor second, major second, fourth, the tritone, the minor tenth, and the minor seventh. Sorry, major seventh. So the good thing about this is that there is a fine symmetry of the set 12. I remember that we're doing octave identification that sends the consonances into dissonances and back. That's what it says here, that you transform with this a fine map the consonances, you obtain dissonances, and if you do it again, you get back the consonances, and not a permutation of consonants, but in the same order. And this one is the fine, the polarity, sorry, of the strong dichotomy. And well, I'm not, I will not tell you here that there is more than one, or the details I would tell you, of course, there are more strong dichotomies. Well, at least you don't take into account the affine images. I mean, you can transform this with an invertible element from set 12, and add whatever you want. This that would make equivalence class on the consonances. But it doesn't. It is not the only one that exists. But I will not delve into that point here because it's not the point. But I will give you some details of how the transfer, or how to transform the consonants into dissonances. So 0 would go to 2 back. If you perform the calculations as third, minor third goes into the fourth, the major fourth into the minor seventh, the fifth into the minor second, to the minor second, and the minor sixth to the tritone, and the major sixth to the major seventh. And again, I think it will go forth and back. But this only speaks of one tone or one interval. We need two things: the cantus firmus and the discanthus. And the approach here is interesting, and this is the interesting part of the model, that you need counterpoint intervals as the cantus firmus and the distance from the cantus firmus to the discanthus. That would go here in the dual part of the dual number idea of counterpoint intervals. And so you have this, you have the cantus firmus. In this case, this would be 2 cos 2. I would write it, but I can't with the pure PDF. And you would add the distance, this arrow. You would not put here the 2 again. It would not be 2 plus epsilon 2. No, it would be 2 plus epsilon 0, because it's an octave. Octave. I'm not sure. And this is the original dual model idea. So the group of counterpoint symmetry, sorry, for the counterpoint intervals are of this form. You have here an invertible element of the dual numbers. It only needs to be invertible. This one could be arbitrary of whatever of set 12, element of the set 12. And here also it's any element of set 12, epsilon, the dual numbers. And I think, the notation, standard notation for all the transformations of this form is a general linear group, a fine general linear group of this ring. And so for an arbitrary dichotomy, I told you there are more than one, but you can think of this as the original consonants and dissonant dichotomy. And the set of all consonant intervals is that you take any cantus firmus, but the distance should be a consonant. And all the dissonances are the other part. You take any cantus firmus and a dissonance as a dual part. So there is a canonical symmetry, P sub C, that exchanges the consonances, the counterpoint consonances into dissonance and back. And this is the induced polarity. The problem is that it's not unique. But the one that we want is in a certain way unique, that it preserves what is called a tangent space. But this is not indispensable for our discussion, but it's good to know. And it's good to remember that it's not the only one. It's not the only fine symmetry that changes consonances into dissonance, but when we're talking about the counterpoint ones, the ones that have a cantus firmus and a discanthus. And we let this group, the fine general linear group, act pointwise on the subsets of dual numbers, in this case, counterpoint intervals. And you take one of them and transform all the consonances. These are the GD form consonant intervals, and GD form dissonant intervals are the transformation of the dissonances, of course. And this is the foundation of how we can get the allowed steps in the counterpoint. And this is important because the problem is, how do you allow any tension between a counterpoint interval and an alpha? Because they are both in the same part of the dichotomy. Here, you have to pay attention now. We're not in the original interval dichotomy, but this is a counterpoint interval dichotomy. I mean, here are things that have cantus firmus and a distance, an interval between the cantus firmus and the discanthus. So we are going from one consonant into another consonant. So here we have no tension, or we're going between a consonant and a consonant. That sounds pretty good, but how do you get any tension? That's the main problem that is to be solved with this model. So we deform the consonants and dissonants, and that's what I'm representing here, changing of color and deforming it. The blue part goes into this green part, and the orange part goes into this pink part. But look now that the original consonant now is at the form dissonance. So it's like a twisted perspective of the original dichotomy, and now you have a dissonance, a relative dissonance to these consonants and this symmetry. And then you have tension. You're solving or resolving or relaxing tension from a relative dissonance into a relative consonance, but that is also an original consonance. So we can define counterpoint symmetries, things that do this job with subject to three conditions. And sorry, I'm running a little bit out of time, but I think I can finish. First, the consonant that begins the step should be a relative dissonance, not like this, because if it is like this, the deformation by the symmetry, then this is still the form consonant, so it's not working. I think I made a mistake here with the labels. They should be swapped. Sorry. The polarity, the induced polarity, should commute with symmetry. This is a little bit of a technical requirement, but it's also some kind of that is coherent. The transformation that is done by the polarity. If there is another polarity that exchanges the form consonants and dissonance, like a little bit like, so why would we require a polarity in the first place, and to be extended to the counterpoint intervals? That it would be like superfluous notion. So in order to have a meaning, we require this commutation. And also, this intersection of the form consonants and original consonants should be as large as possible. And this part is admitted successful. So, I mean, all the consonants that are also the form dissonances can go from this part into this part, and that would be the rules of our counterpoint in this world of counterpoint, that induced by these consonants and dissonances. If you change the consonants and dissonance into another or to another different class of under a fine symmetry, then you could get a different counterpoint theory. And this is also a very important feature of the model, that it relativizes the notion of counterpoint, not only to standard consonances and dissonances. And even, for instance, you can exchange the rows of consonant and dissonant intervals, and you get a legitimate dissonant counterpoint. So you can also have you have from dissonant interval, you can go to a dissonant deformed dissonance, and you get tension in this like mirror counterpoint, something that is to be done in contemporary music, but it's like there was no natural logical way of doing it. So we can go now into the second species case. So we need, as I told you, an algebraic structure when I can attach two intervals to a base tone. And quite naturally, we take all polynomials of this formula. It's like the quite natural next step after the dual numbers. You take the ideal generated by the squared variable, first variable, the second variable, and the product. So it allows us to disregard all the nonlinear parts. And of upper or larger degree, and we rename like first like epsilon for the class of x, and second epsilon of the class of y. C would still be the Cantus-Firmus, and this would be the two intervals. So here you are. I have the Cantus-Firmus, one interval for the first for the upbeat, sorry. Not downbeat, sorry, and the second one for the upbeat, right? So this is a two interval, quite natural. And here's where I have been discussing with, particularly with one of Guerino's student. I don't remember his name. Sorry, I don't remember. But it says, well, but why this show? Why did you choose this? Why don't you take the dual, not the dual numbers, or like these two-dimensional dual numbers, but the same polynomial ring of one variable, and you discard all the elements of degree 3 or further, and say, and it would basically work the same way, and say, well, yes, in principle it would, but there are certain extra features of the model that perhaps would not be preserved. I studied that problem long ago, and I concluded it is not the most natural choice, but I no longer reconstruct the way to do it, and but I think I will need to do that. But for the moment, this works, and we will not have symmetries, and that's a little bit of an error in the paper, that I call them symmetries, but are actual projections, because we're going from going down in the dimensions. So in a 3-dimensional space will go to a 2-dimensional space, and in this way, the idea here is that for a one species case, you can take this square here, and this would act exactly the same as a dual number multiplication. So I add this component in order to have some control of it, but not a total influence. But that's why I chose to take this as 0. And once you perform the computations, you get an algebraic characterization of the commutation of the polarity, induced polarity, and the symmetry. That is just an extension, right, or a perturbation of the original one, of the first species case. So we have a counterpoint projection that accomplishes this by making it this should be a dissonance, relative dissonance, in the form of projected consonances. The square of the projection in the original first species, I would say, counterpoint, and the projection should commute, and this would be the canonical plurality of the first species interval, the successor, and the cardinality of the intersection is maximal among all that is possible. So everything worked fine, at least from the theoretical view. In the first species case, you prove that you have to perform all the calculations based in the Cantor of 0, and then translate properly. So this is essentially what it says, the theorem here, that there is a special projection that can do all the work of any other projection, and you can check the Cantor of 0. So you have only to check the first, the downbeat interval, and then the upbeat interval, but you have to check that there is a different set for each consonance that each potential dissonance, or the second interval. You have to perform a calculation for each of them, and you have a counterpoint theorem that every interval has at least k squared in set of 2k. In this case, it would be 36 in the classical case of set 12. And at most, I don't remember, this 2k squared minus k. I think it's 48. I'm not sure for set 12. But in general, it is the same. And essentially, it preserves, when you check all the output of the algorithm, of Hitcher's algorithm, you see that basically preserves most of the prohibitions. And actually, if you check the first example, valid example of second species counterpoint in the graphs ad Parnassum, and here you can see the intervals. I will just show you a couple of them. Here you have 2, this because it's a D, and the interval from D to A, it's a fifth, and then you have here an octave. So that's what this is 1 is 0, a fifth and an octave, and also here you have F, that's 5, and a third, major third, so it's 4, and a tritone, that is 6, and so on, right? And by the way, this is, I say the first ballot because before that one, there is a student attempts to write second species by himself, but he makes a mistake of putting something that when you disregard the second interval, well, the upbeat interval, then you have parallel fifths. So that's why the teacher says that it's not valid, and it's the same. It have the same projection model. So this is a good thing. Also, it's nice because it's also for the. I remember that for the Octava Batuta, also it works for the in the Fuchs. Sorry, in the first species model, it works as is intended in the Fox treatise. So, well, I put a little bit of detail, but I'm running out of time. This is a consonance, and if you transform it with the reaction, you get 5/4. So that tells that it's valid to take that to interval. This interval can be defined arbitrarily. You can take it what you need for the purposes of the melody or the counterpoint. Of course, this one should also work with the next interval, but I would say that that's the problem of the composer. So we quickly compare this with the Fuchs approach. I would read this one. The second species results when two half notes are set against a whole note. The first of them comes on the downbeat and must always be consonant. The second comes on the upbeat, and it may be dissonant if it moves from the preceding note and to the following note stepwise. That's the main restriction of the second species, one of the main restrictions. But it's, I would say, it's natural for our model because we don't take into account melodic considerations. And so, however, if it moves by skip, it must be consonant. But I would say this makes a lot of sense if you are going to sing this, because if you want to sing a dissonance, it's much easier to do that if you are moving stepwise. But for an instrument, it makes exactly the same case to do it whatever you want. So, but well, anyhow, we take this step of the zero. I remember that we can concentrate on the zero case and to another one. And we check if the second one, for the first case that I call here first case, if it is stepwise. So I allow it if it connects to a valid step in first species, and the second at the upbeat of the first interval, sorry, to interval is connects stepwise to the scantus. And the other one is if you have a consonant in the upbeat, then you check just that if you duplicate the cantus firmus, you get a valid first species progression. So when you do the calculations, there is a GitHub. I have in my GitHub account the code for the computations. You get this number of case one possible sequences, and this for the second case. And as you can see, the projection model covers most of it. What Fuchs predicts. We're taking the simplification of Martini's simplification that you are not allowed only direct movement into a perfect consonance as the criteria for checking the validity of the first species Fuchs model. So Fuchs can the things that the projection model cannot explain, but only Fuchs can. It's only 6.8% and 4.1% for case 1 and 2. So I think it's rather acceptable. And to say, well, but the problem is that you accept most of the things, of course, but this is also a problem of the first species model. It also accepts most of the progression. That's why we take the same approach of Martini, that we're checking what is not allowed, not what is allowed, because most of things are allowed. And also it's what Juno did for his when he makes these graphs of the counterpoint worlds, when you check all the allowed steps, it's easier to just draw what is not allowed and not what is not allowed, what is allowed, because it's a much smaller graph. So here are my references. There is of course more in the article, but I just want to call your attention to the Mazzola's original formulation of the model. Here's my extension for the general microtonal counterpoint. This also is microtonal second species counterpoint. Here's a source of the Fuchs approach. What we use like the canonical reference, and the computations for first species, where I take this 89.7671% is from Nieto's calculation for his BS thesis, and well, that would be all from that's it. Thank you very much. I don't know if there is some time for questions. I run out of time a little bit, I think.
There's a question, yes.
I have two questions, if that's okay. Can you hear me?
Yes.
Okay. First, I was just wondering about the, I think what was it, the affine transformation that takes you from the consonant intervals to the dissonant intervals and back. I was wondering, I didn't quite see why it was necessary for that mapping to be affine. Like, I was just wondering if we could do the same thing with any idempotent mapping between the consonant and dissonant. Or actually, that may have answered my question. But yeah, I was wondering about why it needs to be affine for that to work.
Well, yeah, fine. It's a choice among many, but it's a general framework of the topos of music, and it requires some justification to restrict oneself to find. But you can actually extend that. There is an article in the contributions to discrete mathematics, when I consider the case when you can take not only affine symmetries but also relatively arbitrary polarities. But I actually, well, you studied the combinatorics of the problem, but in principle, as long as you have the three conditions for a polarity, you can do it would work in principle with general transform.
And then my second question was, when I think about doing counterpoint, I've always wondered, is there like a computational sort of backtracking algorithm to compute, a valid counterpoint? But, so when we discussed this, it seems like, we talked about the fact that these conditions are necessary for the counterpoint, but I guess I didn't see a lot about, sufficiency. So I guess I think this might have been the last table when you showed counterpoints that were valid only for this model and not Fuchs's model or something like that. I was wondering if you took a look at some of the ones that are valid only for the projection model and looked at, what things exist only in the projection model but not Fuchs's model, and why that might be.
Yes, I did. But I did not take note of it in the article, but you can actually see the output and check it. But I remember the thing that I remember is that mask relatives are not allowed. I mean, if you take away the upbeat part and you get parallel fifths, that in general is not allowed. And you cannot go in the cantus firmus and skip and try to skip is not allowed all times. So I remember that's the general pattern, but but you are right. I remember seeing it for a while the valid the projection mode of valid only progressions, and I don't remember spotting a particular pattern. But I think it would be a nice project for a sequel.
Okay.
Okay, I think we should stop now because Gilles is coming now. Octavio, thank you very much.
Yeah, thank you very much.
Thank you. So we have 1 minute to Gilles to come and install his.
I'm here. Oh, Biden.
Well,
Yeah.
it's a great pleasure to introduce our great friend, Gilles Baroin, from the University of Toulouse. And he will speak us about, and I leave you to tell the title.
Did you remember my title?
Yes, yeah.
Yeah.
When the virtual reality helps fathom musical
Yeah. And fathom hyperdimensional model. Hello, ladies and gentlemen, dear friends. I'm really happy to be here. I owe you and apologize for yesterday because my jokes were made for Georgia. Okay. Now I'm gonna explain you. In US, you have different states. You know, each state has a symbol as an anthem. For instance, you have the Lone Star State for Texas. Here is the peach state. The peach is a fruit. When it makes a joke, we preach. Like Madonna Papa don't preach. If you remove the heart, it makes peach. Okay? Sorry, because I will never be, I always want to be talking. So, if we go to the museum here, so in the museum here, you will have on the first level you have the big mouse fish. I don't need the sound. Where is it? Where is it?
Bottom left.
FN? Okay. So. So each state you have a symbol. On the first, I said I had a big mouse. I said a large mouse, bass. Bass, it's the name of a fish. Se llama la carpa, une carpo. It's the name of a fish. So large mouse, fish. Okay, it's in the museum on the first level. Vas-y. So you will have the first symbol of Georgia. So in the virtual museum, when you go on the second one, I made a joke with the bee. I say, oh, honey, let it be, not let it be, let it be, because the honeybee is the second, one of the symbols of Georgia. So by the way, we can visit the museum. It's organized in different levels, depending on which difficulty we have from the model, how many dimensions. Then when we came to the third level, this is the Cherokee rose, another symbol from the peach state. And on the last, you will tell me the name of the brown? It's a brown.
Albert?
Yeah. Not the name. So, I was frustrated. I'm working with Stéphane de Girondeau, who is a composer and is teacher, professor of composition in the Conservatoire de la Ville de Paris. So he's teaching composition there. He's very well known, he's making a lot of installation, and we met together to create different mathematical models, such as representing spectra into hyperspace. So I won't explain you what is Mathemusic, but we will go, for people who doesn't know me, just consider it's like a tonet. It's a zero decomposition of the 12Z3 cross Z4. I just made it for my PhD on as a product of two graphs, Cartesian product of two graphs, then with a spectral projection of the normalized Laplacian. And I got a graph that's called the planet graph. That's a product of here. It will be, it can be, of course, project on a model like on a torus. It's the same way that other people like Rick did, or Guerino, Mazzola, or Thomas made it with, I think, with T3, T4. So it's just another approach. So I use quaternions. I'm working in 4D space. Tutti i cammini portano a Roma. It's not Rome, Georgia. Okay, so it's virtual reality. It's quite a new field. The subject is to help fathom the reality. When you are in a space, you have possibility to manipulate objects, to move within space, and to get the sound from the object. I've seen the eyes from my fellow musicians here. When they went into their own model, how they discovered it. I saw Maria and Manu, and they were inside, and you see you're into the model, and it helps understand how it works. The first subject of my paper, I've been working with Ildar Kananov. It's from the Peabody Institute in Baltimore. Symbol?
Orioles.
Good, you know. So, it's from Peabody Institute. I met him, I think in Serbia. I made a lecture in his university, so remotely, and then we published a paper. And that was premiere in the Conservatory of Moscow, so before the war. I will show you how it works, and made an application from this onto the virtual reality. You are welcome to test it in the virtual environment. So I shut up now. I be quiet. It's free speech, but. So I don't spoil you the end. Principle of this, when we created a toolnet, you can, of course, already know that. I use my coloration in 2 dimensions. One is the shape, so all the spheres or all the squares. The other dimensions is the color, so 2 lexical dimensions for 2 directions, x, y, or alpha, theta in a hyperspace. We use what we call, here there are different colors, depending on the transformation. Next extension was adding what we call spider web. When a spider returns home, was presented in Madrid. There is no tonal, there is only one tonal center here. Just a few musical words. Was working with Hugo Ceres from Hungary. He's in university in Brest in France. I said I love this Tchaikovsky. He said, but there is no move here. What's the point of having a tonal center when you stay in B minor? And then we discover that among this piece of music, it will make a journey and let us explore all possibilities we have around one. So you're welcome to come to my website and see other examples for this. And this video, when we go back to the virtual world, yeah, let's go back to the virtual world. This is projected now on a sphere. That's what we call a spherical projection. Usually you call it 360, but it's a 4 pi steradian. So it's on the whole sphere. So you will sit, you will try with a headset, and you will be inside of this. And you have a better perception than on a, of course, on a flat screen. That was for the first, to demonstrate here. Oh, of course, the subject was to keep path, it's in my paper, of the track. Well, when we went here, he said, okay, but I want to see how long you take from one node to the other one, from one position. And for this, I use a computer graphic trick, and I use, in a graph theory, it's called activity on nodes graph. Means how many time you spend on a particular task. And I just do it graphically by putting some sand on the path, so the more times you use this path, the whiter it's going to be. And then you have a whole picture of a piece of music, and it's done to compare, to make comparison from this and this. It only works in 2 dimensions. When we do it in 4D, doesn't make sense to see any path within a hypersphere. It's better on 2 dimensions for this. We had a lot of questions we had for when we started. The first time I was in Paris, the sphere you saw with Beethoven was very easy. And then people asked me, can you make any type of chords? We said, yeah. And we did a representation of fathom in Paris, and they say, okay, can you make spectral music? Yes, we can. You know, Barack Obama said, yes, we can. So, okay, somebody's following, I love it. So, no, we had what we call a chicken. It's a chicken wire from Jack Dosset that we put on the hypersphere. Then we can represent any toneheads, and they ask me, what if we don't have equal temperaments? Okay, no problems. We just deform the hypersphere. Then I've introduced the cube dance, and the last one we have is called the untangled hypersphere. That's what we are going to see right now. With Stephanie had the need to say, okay, I stopped working with this, it's too classical music, there's no modern composition, you should go microtonal, you should go hyperspace. Okay, let's go, let's do it. And so we went here, and we had the idea to untangle 2 hyperspheres. One is tuned on a 440 Hertz, and the other is -1 quarter tone. When you play, I think you guys know, on a quarter tone music, we have usually 2 orchestras. One is tuned on La, and the other is La minus quarter tone. And with this, you can have a song. So just 2 hyperspheres that are untangled. We just love this word, untangled. So, comment c'est dit en français? Intriqué, la intrication, like you have in quantum mechanics. It's not quantum mechanics, just the position of the hypersphere's position on here will depend on that sphere and that sphere. By the way, if we can do it in 4D, I can do it in 2D, so it might be possible to project on the terrace. I didn't have time to do that, but I think you will come to my house in July. We try to do something representing, of course, on a Klein bottle or whatever surface you like. So, mathematical virtual museum. Let's have a walk. Scusi. Okay. This is, I will explain the idle music. In the virtual world, each tone, each object, each item is representing whatever you like. Here I'm working for the Taurus of Fezi from Jason from Misery, from the great state of Misery, and Emmanuel from the great state of Catalonia. So, here you can move within the plane on each object. What you see it is filled with my headset. So you might be a little bit busy. So what's important to know that you're able to choose which type of phase you'd like to show. If you want to show this type of chords, here's the type of chords. Here I'm working with the 6/4 chords on minor 7. So as they say, everything is possible in Pakistan, my friend. So here, just do it. We can have a model. So I've tried to make it on a plane. It's infinite planes that you guys know, like the plane. I want you to see the torus. You can have it vertically, horizontally, or flip the axis. Because in Guerino Mazzola model, his alpha angle is the contrary of my alpha angle in my planet model. So here you can switch which way is x, which way is y. Don't ask him why, or just ask my x. No? Okay? So this is navigation, because Emmanuel told me, in my space, I want to go in one direction. I want to fix what we call, I think, a slope. So you can adjust the slope with whole numbers, 3 divided by 5. And since I was working in aviation, I put a heading on a speed. So in the torus of phase, you will move, the torus will rotate in one direction. For instance, this is 90 degrees. I said go west or go east. So you see in a hypersphere, it will only rotate around one axis. It's to make it easier, only rotate on X. Yeah, so each time you encounter an object, you hear the sound. If you have 107 on it, may correspond to Do sharp, Do and Sol, I think. So let's go back to the torus here. Here, you can use this model to discover and to find that all these phases are on the same line. They have the same, you confirm, Jason? Okay, thank you. So with this, it helps me, I say to fathom reality, but to understand his model. I didn't really understand what was a Fourier, but with this and projecting onto the torus, I can see they all belong to the same direction. I can see that the major chords are on one line, one direction. You can see that the single are on one direction. This is, it was the Roman style for the object as well. We made the Clampitt. It's just a 4D object on a hypersphere. Let's go back to the torus and walk. That's the way Emmanuel did it. He came to my place, and I couldn't see his eye because he was under the headset, but he was so pleased. So now you're just moving in one direction, and each time you encounter the object, you can do it in real time, move the way you'd like to have it, and display which type of object. So when we talk about mathematics to fathom mathematical objects, the first goal is to have fun. Some people just, really, the first time I came with this model, I sat in my hypersphere just looking at this type of chords and this type of chords moving around. It's like a psychedelic effect, and you just relax. Second step is to learn. There is something logical behind this. My daughter, who helps me for design, she's 10. She has a great idea, we talk about that. She said, oh, it's easy, I understand numbers. And I saw these tonets to people who have no idea of music. I said, it's easy, it's logical. I see 0, 2, 4. You see the logic of Mathemusic with visualization. Just another example, all I'm talking is, this is the Möbius strip, because we had the challenge to be able to walk on a Möbius strip. We did it. And now I just go back to the hypersphere. Full speed.
Exactly.
Yeah. Engage, warp speed, captain. No. So, this is what we can do now with modern tools. Of course, because it's in a computer, I can record movies. I just recorded to show you the way you see it as a user. But I can say to my camera, you're blocked here for so many seconds, you go then this way, you go then this way. and you can reconstruct all the movies I've made easily and change the past, change the view. If you need a torus, you switch to the torus, you say at this time I want to see that, and a movie will be produced. Once upon a time, a long time ago, we used to use that drawing like Walt Disney. Then we came to 3D, it was cheaper. And now, filmmakers are using Unity, so that's the name of my software, on virtual reality to build the scene. So everything is built as a virtual, as you will be a virtual guy, you will be a virtual woman, you will be, and then inside this world, they just shoot the movie. And if the director comes and say, oh yeah, I don't want to hear, please put me some more light and redo that, and I want that explosion. Now, they will do it in the virtual world directly. So the virtual world, I had to go in my career to go for this type of technology. I started with the 90s, with 3D Studio Max, with 3D pictures, and now I had to switch completely this technology to be able to integrate more easily another model. We talked with if you need to integrate another 4D models, I just need to change the equations. Project into a sphere or to a torus is just changing to parameter. The hard part of the job is to learn how it works, to learn how to put the elements, how to draw, how to interact, graphical user interface. But the really interesting part, that's for me mathematics, how to project to a Clampitt or to hypersphere. It's just a few lines of code. So with this, now we have a tool to integrate any model we'd like to. The Untitled Chapter. So what's the purpose of this virtual results? For fun, to educate people, to experiments, like if you go to your own model, see how it feels when you're inside, and for research. I could have made a paper, I don't know, Beethoven on the Clampitt and publish it with Rick. We go to the Clampitt. It's just, you can integrate whatever you want now. This is a research tool for us. So as a newbie in a world of Jason and Emmanuel, I can see the purpose of the torus surface. It's used to preach mathematics. It was my joke from yesterday. If you remove the R, you have peach. Mariana, draw a peach here. Okay. On business, of course, you guys in America are better in business than me, but there is business model behind that. So to make learning tools, to make tools for, like learning tool for learning, thank you. To make tools to preach mathematics or application or games, because we are scientists, scientific people. A lot of people, they say, okay, you make music and a nice picture, but I'm not. I'm doing no Windows screensaver. What we do here is research. There is a lot of fundamentals in mathematics beyond here. There's on musicology. And if we come to the market with our reputation, with our room, so we say we know the field, there may be opportunity. The last model, so some picture here, the tunnels. Okay. When I was in Paris, I was very new guy. I was clothes like, super dressed. And then came a guy, he has this type of shoes. Let's see. Who is that guy? Not who is that girl. So, who is that guy? And you told me, Gilles Baroin. And I said, I would have said, wow. Because for me, it was so inspiring. I was a young guy. I was reading the name like Richard Cohn Moreno. I saw the name Thomas Noll, Guerino, Mazzola. When you're just Julian Hook, who I follow. Thomas, where is Thomas? Thomas Fiore. Hi. No, he was not. Oh, it's not here? Okay. So, hi, Tom. So I saw this name, and you meet these people in Paris, and I said, who is that? And that was Chad Gothard. And we talked together. It was so. I was very impressed. And now I'm the guy who has lost his shoes. And I said to me, here are my models, here are the new drawing I made, and it gave me some drawings. So in the Mathematical Virtual Museum, there is a dedicated space from Jack, who gave me drawing made with the hand. And he said, oh, you're doing on a hypersphere. I said, oh, you're doing some 7 chords. And you said, hey, let's have a baby together. Just for fun, of course. There's no doubt about this. So we went on we wanted to make a hypersphere, and we didn't make that. But we had to plan to put his model on the hypersphere. So I've tried, second I made here, the cube dance as it should be. So you move, virtual reality, you're not allowed to go from far sharp to ray, and you can move it. And of course, the cube dance was already on the hypersphere, but for Atlanta, for this event, I've made this. Moreno tried it yesterday, and yeah. So that was my small tribute to someone who was spiritual. This is the cube, of course. The Möbius strip, so easy now. Rick tried yesterday flying on the Möbius strip. You can walk on it, and everything's possible in virtual reality. Okay, so in the virtual museum, as I said, and I can adapt new objects that are already inside. I'm working with, I was in touch with Dimitri Timochko. It was not available. I will integrate the jacuzzi from Frank Jidreski and a new model, Newton Netzer. I'm in touch with some of you here. I'm already built the model from Emmanuel Jason. The cube, you can test it from Maria. Only you will challenge me for the hype. Oh, okay, you know, I didn't have to ask. I know the question. Can you make a hypercube? Okay. So I mean, this is a tool that I want to integrate more of you guys here inside and to make this virtual museum. This will be my next project for the next years. I lost my job in the university, so I'm doing that. I'm paid by the government. I have, how you say, jobless money, so during this time, I could have learned how to speak English in public. I could have learned how to run your own business. Okay, come on. Just go to the web, go to the US, talk to people, travel, learn Unity, learn something new, and just let's do it. I think I had enough time for questions. Oh no, of course, the hypersphere of the Tori. You saw the Tori yesterday with Ray Charles. You know, in all my models, in contrary to Dimitri Timochko one, when you move inside the space, or in the Tori surface, you move inside the space, I stay. I am the reference point. You can move in the Tori surfaces, but I stay and the torus moves around me, because you cannot move in 4D space. Yeah, somebody tried. That's already the movie, but and it's the same. If you move on the torus, it's nice to be inside, but for me, it makes more sense to have the model rotating in front of you. If you want to see my haircut, it's better I rotate in front of you. It's just logical. So now let's go to the craziest we've ever made. Planet Beta EU. Okay. I've put Roswell, Georgia here, because it's the most strange we have. So this is the hypersphere of the entangled one. You have two spheres. So this is to explore what it is to be in a 4D space with program. This is the last one. It's finished in 2 minutes. Sorry, I took too much. So you have one sphere. You can choose the model what to display. So I will go faster. You have integrated TV, the user view, when you size what we call the chords here. So one sphere, one model on one tonnet is with do, re, mi, and the other with do plus, re plus, mi plus, or plus. Voilà. I made it short.
No, I think you made Alexander Scriabin's dream almost true. So happy to see, except for one thing:
Tell me.
perfumes. You
Perfume.
know, Alexander Scriabin think of not only lights and words, but also on smelling.
Let's do it.
But you can. Yeah,
You want to do it?
of course.
If you master perfume, we can arrange something in the virtual space and
We don't have
perfumes moving around you.
I never have.
Yeah.
Well, anybody wants to? I'm sure there are lots of questions, but we are short of time. So short question.
Yeah.
It's not clear for me how are you moving in the model from chord to chord. That's my first question. Okay, and the second is for the future. Do you think that do you want or do you know how to extend this to just harmony?
To?
Just harmony.
Just? Okay.
Just
So,
as-
to answer the first question, when you're in the virtual world, you move like in the real world. You can do this, go around the notes from here, that. Then, I used to move with a joystick like in a video game. Instead of shooting bad guys, you just move inside and you hear the sound. So I move with a joystick in
But
the
you
world.
you are the one that
Yeah, I'm the player.
Okay.
It's a game, it's a first person view, and I am the player, and I'm moving in the space.
Okay.
For jazz harmony, yes,
So
everything.
in the first question, you don't have like a criteria. You move freely.
Yes,
Okay.
the only criteria is aesthetic criteria. I have to make this fathomable, so I must be in a hypersphere that I can move into. So just to adapt the size, because you can have any size, adapt the size to your size.
Okay.
It's not a problem. Second question, just harmony, yes. How? Just provide me the model.
Okay.
Okay? We did it for spectral music, for microtonal. And if you have the model,
Yes.
and second question, collaboration, si senor,
Okay.
in Madrid. Muy bien.
Anybody else? Well, we thank you, Gilles.
Yeah. Yeah.
Emmanuel.
Perhaps you could explain quickly how you managed to have the user move on plane representation and not fall over, and like when you have.
Okay.
Excuse me
Just-
on this side, because the machine's too loud. Can you say it again, Emmanuel?
He said because when I'm moving on a plane, if the plane is vertical, I have to have an artificial floor that's invisible. So you are not. You can, of course, I can make a model to fly, go up X, Y, Z, but it's too complicated. It's better if I stay on the ground with the possibility to fly over a model and rotate the cube or the torus. Okay, merci. I love it too. So we make it. It's perfume.
Perfumes? That's
Okay, the next speakers are David Orvek, who is a graduate student at Indiana University. Indiana University. And David Clampitt, who is at the music department of Ohio State. One other thing I just wanted to mention is that we are recording everything, so you will have access once again to see all of this. This is me.
is over.
It's a test.
Is there a way to turn it down? So I'll just do it. Okay.
Not displaying.
Yep. All right. Thank you all for being here. Excited to present today. I'm David Orvek, and we'll be presenting today on sum classes and quotient generalized interval systems. So I'll be doing a short introduction, kind of laying the groundwork for our project, the scholars that we're building on, and kind of what we're doing with that prior work and where our project fits in. So we're starting, our foundation here is a work of Richard Cohn and Robert Cook from the late 90s and early 2000s. They measured voice leading between triads is what they were interested in. And the way they did that, to measure voice leading between two triads, they would basically just calculate the total interval traversed by all three voices moving from one triad to the other. So you would get basically an integer, mod 12, as the result of calculating the voice leading between two triads. And what they found was there was a lot of duplicate values when you calculated that value between any of the 24 major and minor triads, which is to say that there's kind of certain triads seem to live together and would lie the same distance from another place. So explicitly, there's a relationship here between the sum of all the pitch classes in a triad and the voice leading between two triads. So if you have two triads whose pitch classes sum to the same value, mod 12, then those two triads will lie the same voice leading interval from any other triad. And so, and then further also, triads whose sums are the same will always have a voice leading interval of 0. So they used this idea to create equivalence classes within the 24 major and minor triads. So there are 8 equivalence classes called sum classes, or later voice leading zones. And basically, these are voice leading equivalence classes. So there'll be 3 triads, and you could go to any of those 3 triads and you'd have the same interval, basically. Cohn also used these sum classes to define transformation classes. So he grouped basically the 24 Neo-Riemannian transformations into also 8 transformation classes based on if they took a triad to the same sum class. So basically an example, the P and L transformations, if you apply them to an A minor triad, for example, will take you to 2 triads that live in the same sum class. So as a result of that, these 2 triads are equivalent from the perspective of a voice leading interval. And then these transformation classes themselves act as transformations on the sum classes. And then Robert Cook kind of expanded this a little bit by introducing a dual group of sum class transformations, which we'll see more about in a second. But basically another way of moving through the sum class space. So to quickly summarize, this is sort of the situation we're dealing with here. Cohn's model lives in the blue box. Essentially, we have triads that are grouped into sum classes, and then we have Neo-Riemannian transformations that act on those triads that themselves can be grouped into sum class transformations acting on sum classes. So there's a kind of multi-level transformational group system here. Robert Cook was sort of living at this higher level of abstractions, just really looking at the sum classes, but he had an entire extra group over here. So there's kind of a little bit of a gap that's left here. Cook doesn't really live down at the level of the triads themselves, so there's another transformational group here that hasn't really been discussed. We'll say what that is, but more importantly, the goal of our project is to formalize the algebraic structure at play in this sum class system, and then to show how that system can be generalized to lots of other contexts, basically. So to show specifically how you could do the same thing for different sum classes, not just triads and trichords, but any cardinality. So I'm going to turn it over to Professor Clampitt, who will talk a little bit about some group theory. Down there.
Yeah, so as David suggested, what our work is really trying to do is formalize and generalize the previous work, put it on a very strong mathematical foundation. And so I'm just going to give a little bit of that background. I'm not going to read these slides, but these are kind of puts me in mind of our session yesterday, the panel on baseline knowledge, and this would be quite likely part of that baseline knowledge. This is the sort of stuff that gets actually suppressed in our article. We just say basically, look it all up in any abstract algebra textbook. This is kind of boilerplate for that, but just to remind everybody what we're talking about. The apparatus here are normal subgroups, the quotient groups that have the normal subgroup as the identity, and then the next slide will be about the basically the first isomorphism theorem, the sort of fundamental theorem of group theory involving group homomorphisms and quotient groups. So basically, I'll just point, I'm not going to read, I'm just going to kind of point to the slides and information thereupon. So with a given group and a subgroup H, first of all, we can always make these equivalence classes that basically a partition of the group into cosets, as you probably know. Just to remind, we multiply, say, a given group element G times the whole subgroup H as the elements, as we do the multiplication across all elements in H, we get all distinct elements. So the number of elements in a coset is exactly the number of elements in the group, the order of the subgroup H, the order of H. Hence, we get a partition into equal, and we can also easily show that they're disjoint, and so we get a partition of G. Now, we can do this on either multiplying on the left or the right, left cosets or right cosets, and just to remind again, in a non-commutative or non-abelian group, these sets of cosets do not necessarily coincide, but if they do coincide, we have the special case of a normal subgroup. And then we can make a quotient of the full group by that subgroup. We say when we have then the set of cosets itself, G mod H basically, or G by H, is a group itself, and we can easily define the product as you see here. So that's just a little review of that, and then this intimate relationship between group homomorphisms and quotient groups is here. And this is fairly fundamental, that anytime we have a group homomorphism from a group G to a group G prime, and this is an onto homomorphism, and you see the other jargon that you encounter there, then the kernel, K, of that homomorphism is a normal subgroup. And moreover, there's an isomorphism between the aforementioned quotient group, G mod K, and the image under the original group homomorphism, G prime. So this is sort of the fundamental aspect, and more of it goes the other way. Not only is any kernel a normal subgroup, but any normal subgroup is ipso facto is a kernel of a homomorphism that we can make from G onto the quotient group. So that's the background. The other background is well known in our field, I think, but just to rehearse it a little bit, the generalized interval system. And we take for mathematical elegance, I think, Lewin's second definition. I think many music theorists arrive at the first definition of a generalized interval system, which involves three elements, an ordered triple. But later in the book, the trajectory of the book, I know when I speak of the 1987 Generalized Musical Intervals and Transformations, later in the book he comes to what I think is mathematically a more elegant definition of a group and a set, or a space, or a family as he calls it, G and S. And G acts on the space, or on the set S. And it rehearses here the sort of, what does it mean for it to act? Not only does it act, but it acts very powerfully. It acts simply transitively, the group on the space. And it's going to follow that they have the same size, the same cardinality. Finite or infinite, there's a one-to-one mapping, and onto mapping. So I'm not going to rehearse all the steps there, but we have just a group action. There, the only thing that is, it looks totally trivial, but in fact that equation on line 4, on the left-hand side, FG is the product within the group acting on the point S, with the element S. Whereas on the right-hand side, F, the group element, is acting on the action of G on the point S. It's actually a non-trivial thing. And then we have the next level acting transitively. There's always a way to get from a point S to a point T. And then finally, simply transitivity means that that mapping from S to T is unique. So we then specialize to the cases, for example, where we have the group being the usual transpositions and inversions, the order 24 dihedral group, acting on a asymmetric set class that also has 24 members. And so this is the one kind of major proposition that makes our paper hang together. It's not entirely new by any means, but we show within the terms here that given a generalized interval system and a normal subgroup of the group G, then we have a quotient group, and that quotient group induces a set S prime of equivalence classes on S, such that the quotient of G by H acts simply transitively on S prime. That is, our quotient group and S prime make a GIS, and it's perfectly natural to then define it to be a quotient GIS, generalized interval system. Lewin also, this, as I say, it's nothing really new. Lewin often implicitly considered quotient GISs in the mathematical preparatory chapter. He talks about congruences on groups. Effectively, we're getting to this idea of quotient structures. He doesn't name it as such. And so Hooke, for example, points out that these are often happening in the book. But then Hooke, in his 2007 Music Theory Spectrum article, defines a GIS homomorphism, and by the equivalence enunciated earlier in group theory, that means he effectively was defining quotient groups as well. But he came at it at a different angle. For one thing, he's using Lewin's first definition. So there's something new here, but not really all that new, but it makes everything else follow. That proposition 2 is completely general, could be finite or infinite, and so forth. But here, we are specializing to generalized interval systems, again, acting a TNIN group acting on a set class. And we have our canonical example of the harmonic triads. And we are interested in quotient groups acting on the sum classes. So recalling Cohn's initial observation that these transpositions, T0 of course, T4 and T8, leave sum classes fixed. We consider that cyclic group. It's easy to see that any cyclic group any cyclic subgroup of the TNIN group is normal, and therefore we have a quotient. We have a quotient group that induces an action on the sum classes, precisely on the sum classes. So in other words, the predicted set of equivalence classes in S prime is indeed the sum classes. And the other aspect of Lewin's theory that we make use of is this duality that he proves that whenever we have a non-commutative generalized interval system, that gives rise to its dual. So we have groups G and G prime as simply transitive actions on S. Okay, that's the parent space, and these are the parent groups. those two groups live in the big symmetric group on S, right? A group of all bijections on S, and as such we can compose them. And the great thing about the dual group is that they are each other's commuting groups. Okay, so as you see, G prime equals G prime G. And they're also each other's interval preserving groups. All right. So given a quotient, given such a GIS, we can find the quotient of group given any normal subgroup H. Then there's also then going to be a dual quotient, and it's only really interesting if we have if the non-commutativity of the parent group is inherited by the quotient groups. And then so the most familiar example here, probably familiar to everyone here, is when we have our usual TNIN group, but also its dual turns out fascinatingly to be the Neo-Riemannian group of acting only on triads. And so that's the dual GIS, and once again, for the purposes here, you can form quotient groups of one and the other. In the case of the Neo-Riemannian group, the normal subgroup is the cyclic group E, the identity PL and LP. They also preserve the sum classes, and we take the quotient. And so we have basically, they are each other's duals in the quotient world. Then we can generalize to other set classes very easily, not just trichords, but all of them. And a passage from involving set class 3-3 will be introduced in a Schoenberg example. But we can construct quotient GISs for some classes, but for all set classes, but sometimes we can't actually use as the parent group the usual TNIN group. It just won't work for reasons that we detail. In that case, you have to use one of these, an abelian group involving the 12 transpositions and one contextual inversion. In the paper, we detail the singular case that doesn't work for trichords. That's the 015 trichord. It's interesting that the trichord that Lewin uses the pentachord that Lewin uses, 5-4, in his Stockhausen Kavistrukturei piece is such a group. Now he doesn't use the whole he doesn't use the whole ornamentum here, but anyway, all these so-called maverick cases are dealt with as well. All right, I'll turn it back over to David.
Thank you. Okay, so to wrap up here, we'll just show quickly a couple of analytical examples to show some of the utility of this dual GIS quotient system. We'll look first at an example with using major and minor triads and then some 014 trichords. So I have here an excerpt from a piece by Charles Stanford. It's a ballad. Fascinating piece that we don't have time to spend time with, but we'll be focusing on this central passage in the text. Basically, the protagonist has a dream, and a very surreal sort of dream, and it's in this passage there's a lot of extensive chromaticism and sequences, so we're going to look at that passage. I just want to make sure the volume here is not way too loud. So give me just a second. Okay, I'm not sure how much power I have to adjust volume. Let me just check something. Hopefully it's not too loud.
I saw the star lips in
Apologies for how loud that was. The next one will be quieter. So in that dream passage, we have a chromatic sequence kind of framing this at the beginning and at the end. And as you can see, the beginning sequence is all minor triads. This is just reduction. The ending sequence that we just heard very strikingly is all major triads. But there's some interesting relationships between these two sequences. So these are the triadic subclasses. Each subclass contains 3 triads of the same quality. So the opening sequence effectively moves through all the subclasses containing minor triads. The closing sequence moves through all the subclasses containing major triads. So then if we just add that information back on here, we can see we move through several of the subclasses more than once. But if we want to talk about these passages transformationally, how they relate to one another and how they move within each sequence, we need to add some transformations. So this is where the transformational groups come in. So this is the quotient group of the usual transpositions and inversions. So the quotient group moves between the subclasses. The transformations at the lower level would move between the triads. But there are 8 basically different ways of moving through these subclasses. Then there's also a dual group, the XY group. This is Cohn's original group, showing the kind of contextual way of moving through that same space. So some of these transformations are more or less the same, or actually exactly the same in their action, but some of them are quite different. So we can use these 2 groups, because they're commuting groups, to make this nice commutative diagram showing basically the green transformations within each sequence show a consistent voice leading that's being preserved through each sequence. So although there are 2 transpositions at the chord-to-chord level, at this larger level of subclass, there's only 1 transposition, which means the voice leading is always the same. And then the red transformations are showing that there's a consistent contextual inversion, basically relating each triad in the same position in these 2 sequences. So we can see this is a very strong relationship between those 2 sequences that sort of bookend that passage. And then quickly I'll show a similar example using O14 trichords from a famous example by Schoenberg. There are obviously strong affinities between O14 trichords and major and minor triads. That does not need to be the case in order for this to work. It just happens to be a good example. You could do the same thing with O13, for example, and it would work as well. So this should not be as loud as the last example. So the passage that I've boxed here in red, that's a sequence, descending sequence of O14 trichords, which I've created a reduction here, basically just moving back and forth between prime and inverted forms of the O14 trichord, and then the right and left hands sort of follow each other, transposed up a ninth. In some classes we can see here we're just moving between 2 subclasses within each and adjacent subclasses. So to make the same sort of transformational analysis as we did for the triads, we need to basically bring over those groups. So the TI quotient group comes for free, sort of, because those transformations are already defined to act on O14 trichords or any pitch class set. The XY group, in order to bring that group along, we would need to define a contextual inversion and transposition to act on an O14 trichord. And there are, in fact, any number of ways to do that. Really, any of them will work. The requirement, basically, if you want the transformational group to remain, its actions to remain the same at the level of the subclasses, this is just reproducing the earlier slide. You would just have to find a contextual inversion, or define a contextual inversion that would move you between the trichords living in adjacent subclasses. So once you've done that, whatever your transformation that lives in X0, as long as it kind of follows that condition, the rest of this will fall out naturally. So in effect then you can just copy over everything with some small adjustments, and you can create a diagram again like this, borrowing, if you need to, transpositions or transformations, I should say, from both groups, and create this nice commutative diagram relating them. So in conclusion, what we've shown here, I think, is that the system is very powerful. It can be generalized, as we've seen, to be applicable not just to trichords. You could do the same for other larger set classes as well. This system effectively gives you a set of ready-made tools for lots of different analytical situations, so I think there's a lot of utility here. And then something that we didn't have a chance to explore today, but I think is an interesting idea to explore, is ways of comparing things in different universes. What do I mean by that? you could analyze a passage that uses major and minor triads, for example, and then also maybe O and 4 trichords, and you can see the way, if you can kind of put them on the same terms in terms of sum classes and their transformations, you can see the ways that composers work through the same ideas in completely different harmonic languages. So I think there's a lot of potential there to explore further. So if we have time, we'd be happy to take any questions you have.
So the use of the sum of the differences in notes to calculate the distance between chords, that comes from the Conan-Cook.
Yes.
I'm wondering, did they or did you explore it all using other methods, like maybe the Euclidean norm? In case you thought maybe the bigger distances between notes mattered more than the smaller ones.
We have not.
I'm not aware of anybody doing that. It would certainly change a lot of things about the system, but I imagine it could be adapted. But yeah, the kind of sum class interval is a very abstract and kind of general way of measuring voice leading.
And the quotient structure is completely general. So if it would fit with a group in a group theoretic foundation, then it'll work with Lewin's structure, and all this would carry through.
Sure, so you're agnostic to it. Just
Other metrics or.
So by the bigger distance, do you mean as far apart as possible rather than as close as possible? Is that what you're referring to?
Yeah, like another way you can measure distance between chords is only focus on what's the biggest interval. And that would just be taking the max, where somewhere in between would be like square them all. And
I've got a couple of pages in Audacious Euclid where I kind of explore. I can point that out to you. It's in chapter 6, I think.
Thank you.
But it's just set in direction.
And my question is kind of another version of that, which is the sum classes turn out to be really important in voice leading spaces, right?
Yeah.
And those are geometries and they're metric spaces. The reason they're important, I mean, you could probably say this also, is that they're basically the factor out transposition. What you're left with is an equal sum class. So I wonder, I mean, I see that you have a master's thesis on this, and maybe you've talked about that. And maybe you could say something about, the group theoretic perspective. I think is probably just is that abstraction of what's happening in
Well, this is formalizing, what people have already been working with and analytically for quite some time, just making sure it's all kind of nailed down. I think, Rick, when you first did it in 1998, I guess it was, you sort of jumped right into the quotient. You worked at that level, and it was very, it was inspiring to David for his master's. Yeah, Emmanuel.
First of all, I would like to underline that this is really the kind of paper I like, because there is understanding mathematics, and the group theoretical aspect is something that really works and functions well, and there are musical applications just behind. So that's wonderful. Well, and I couldn't help but notice that the trichord used in the Schoenberg, it's not new, but if you multiply it by 5 or 7, you get...
But this is what David was alluding to when he said there's a close connection between the normal harmonic triads and 014, but it's not necessary. We're not making use of that multiplicative. It is very interesting.
Maybe you could, because I'm sure with the algebraic definition of your quotient action, or action of a quotient or whatever, you can compute the relationship a priori between what happens in certain triads, and I think Thomas Knoll called them jets and shocks, those trichords.
Yeah, in my master's thesis, I sort of broached that topic, like actually defining a transformational system where you have the 014 trichords and defining a transformational system to move between the two groups.
That's the idea. I think that would be a really powerful application of your definition.
Yeah, I think I kind of start to do it in the appendix to my thesis, and I ran into a problem and was running up against a deadline, so I just left it there to be explored further. But yeah.
I kind of hijacked the running of this, but so there are quite a few questions, but we're kind of running. I will let you.
I think we're out of time.
Say one more.
Well, one more question, just a short question, because otherwise we will be Who has a short?
Tom's got one in the back.
Yeah, has a short question.
Yeah, quick question about when you constructed the dual group of the quotient group. Did you posit any relationship between H and H prime before forming the quotient? For instance, is H prime going to be the centralizer of H?
So if H and H prime have what?
Are they related in any way? Did you posit?
Yeah, well,
any
yeah, I
relationship
mean,
between them?
I think in your example, you were saying there are many maybe possibilities for the dual, but I mean, I think basically it is kind of forced that we have a group and the dual group. We have our TNIN group and we have the Neo-Riemannian group. They're the duals, and I think that gives rise, I mean, you choose your normal subgroup, and our theorem 2, or proposition 2 says it basically forces the set
Sort
of.
of no matter what contextual inversion you chose, you would get something like this, but
Yeah,
the
like
specific
this.
actions would be kind of rotated, but you would still
Right.
get 8 transformations like this.
Right, yeah,
Yeah.
I think the subdual group theorem, we have a couple of years ago, Thomas and Roman and I did a subdual group theorem. I think it might be handy here.
Yeah, okay, yes, right, because, right, to make that really clear. So it's not absolutely unique, but it's effectively, they're gonna be isomorphic for
Unique
sure.
up to conjugation probably.
Yeah, up to conjugation, I think that's exactly right, yeah.
Great, thank you.
Yeah, good, good, all right, thanks very
Well,
much,
thank you
everybody, thank you.
all. We take 1 minute, so Greta and Ludovico, I don't know them, but they are here. Greta and.
So Greta is in Italy, normally is by Zoom.
Let's go by Zoom.
Yeah.
They should be online.
Maybe they're preparing that.
Yeah.
I have a question that's more ignorant to music theory than is TN slash actually or
It's not about transpositioning the version operators. Slashes in situations like that where it's not. Something like